session to ensure that we go out in real style. We have three of the truly top star names in this area. Marjan, Karen and David, and Marjan's going to be the first to speak. Marjan Sjerps from Amsterdam.
So, no pressure, right? Well, that must have been the best introduction ever to me. Thank you very much. Thank you also for inviting me to speak here. I really appreciate the atmosphere and the group of people that are here. I think it's very nice. The topic of my presentation is entirely different, I guess, from what the rest of the speakers have been presenting. It's going to be on tire marks. And can you hear me in the back, by the way? Is it, yeah? Okay. It'd be good to have a mic. I do have a mic.
Oh, you do? Okay.
Yeah.
It wasn't very loud. Anyway, keep it.
Okay. Most of you will have heard of the PCAST report by now. And the PCAST report is worried about feature comparison method because of the human factor that comes into play for these kinds of methods. So they were saying, well, because the individual steps are not objectively specified, the method must be evaluated as if it were a black box. And evaluations of validity and reliability, so these are key things to them, must therefore be based on black box studies. And they propose to invest a lot of research in these black box studies. And also they would like to get error rates from them. Now I think that's maybe not the optimal way to go forward, because these error rates are sort of general error rates, but it depends very much on the case. You have difficult cases, you have easy cases, so you have different types of cases, so therefore different types of error rates. And also this whole match, no match approach. Well, Jeff Morrison has written a paper about that. I fully agree with that. That's also, we can do better than that, I think. We can do better than this black box match, no match approach and then give an error rate. And today I will present one idea of how we may advance the field beyond this. And I will illustrate it with a tire mark case. First a disclaimer. So it is based on a real case, but I adapted it for this presentation. So therefore there's no conclusions whatsoever for the real case. This is the tire marks in question. So the case was that there was somebody was threatened and also beaten up in her own home. And she was a very important person. So this was a real serious case. And although they had lots of evidence, they had DNA evidence and all sorts of evidence, but they were also very interested in the tire marks. So the crime scene was the home of this person, and she had a grass in the garden, and what you could see was a whole sort of set of tracks from a car on the lawn, and also there was this tiles on the terrace, and there were some tracks as well on that tiles. But they were really not very of good quality. So here you see the best mark that they had in the grass, and here you see the best mark that they had on the tile. Now I don't know if you can see any pattern on it. When I first looked at that I thought, well, nothing there, you know, what's there to compare? But if you show this to a tire mark person, there's somebody in the back looking at the pictures, all right. If you show this to a tire marks person, they see all sorts of things. So they see a pattern here, and they see all sorts of characteristics here. So I guess that's why they're experts and I'm not. But so normally the procedure is that the tire expert would look at what we call class features. So these are the tires of the suspect's car, and you can see a number of things which are just production features. So every tire in the same production line has the same features. We call it class features. So you could observe some of these features apparently in this grass, and some of these features apparently on the tire. So I call these A and B, whatever they are. But normally this is the start of the investigation. So they would check if the class features are matching, and then from there they would look at acquired features like tears and cracks and wear and all sorts of things which would sort of be special to this specific tire. But on these marks they couldn't see any of those. So this case was done by a police expert, and this police expert said, well, the class characteristics they match, but I cannot determine whether it was this tire because I don't see these acquired features.
Is there anything significant in the absence of these acquired marks?
No, because it's just, it's on the background, that's why you cannot see them. So you cannot infer anything from that. If you have a really good quality mark, you could. Yeah. So I was involved in the case because there was a defense lawyer, and he asked a whole bunch of questions, and one of them had to do with the frequency of the class characteristics. So he asked questions like how many of the total number of registered personal cars in the Netherlands on this specific date had access with a track width, because you could also measure the track width on the lawn, of about 144 to 145 centimeters. How many of the total number of registered Peugeot in the Netherlands, because the car of the suspect was a Peugeot, how many of the total number of registered Peugeot 208? So he went on, and he had all sorts of questions. So I think the field of forensic statistics, the first important thing that we can do is pinpoint what is the relevant question in this case. You can ask all sorts of frequencies, but what is the relevant one? So we start by defining the hypothesis, right? So fortunately I had 1 and 2 instead of prosecution and defense. So the first, thank you. The first one was that the car in question, the car of the suspect, made the marks on the lawn. And the second one is that some unknown other car made the marks on the lawn. And then we go on and define the observations on the crime scene. So we could see several things. The profile type of the front tires of this car differed from that of the back tires. You could see that also from the track. The different tires. These two tire profiles have class characteristics A and B. So that's a little bit weird because I cannot see them, but apparently the tire marks experts can. And the access width lie in some sort of interval. And then you define what you see on the suspect's car. So you could also see the profile type of the front tires differ from that of the back tires. They have class characteristics A and B, but you also see more, of course, because you have a nice picture of the tire. So you see lots more details. And also you can measure the axis width really accurately. And it fits interval. So then you can move on and define what's your likelihood ratio, what's the evidential value. So in this case it's a sort of very similar to DNA, I guess. You have the probability of the suspect's vehicle tires, and given that, what's the probability of observing the things on the crime scene. Now assuming that this is 1, this ratio, and this is also 1, then we have here what's the probability that a random car has tire profiles matching tire tracks and has corresponding axis width. So that is, I think, in this case, the relevant question. So then you can sort of split that question into different things. So you have the probability that the axis width match the interval, the probability that you have different tires on the front and on the back axis, and the probability that some tire of a random car matches the first profile. So they have class characteristics A, and then the other one have class characteristics B. So how do you combine them? Well, if I make two assumptions, given that the front and the back tires of a car are different types, I'm assuming that they're independent of each other. So it's not like these two pairs of tires with A and B characteristics are on sale together, or they're more likely to be combined.
I mean, I'm not a tyre expert, but I think there are two different kinds of tyres, and you're not supposed to mix them on the same car.
Yeah, it's a summer and winter.
No, radial and something else.
Yeah.
So, I mean, given that even though they're different manufacturers, you'd have to have the same type. So that would introduce a strong dependence.
Well, I asked different tire experts, and they told me that this was a valid assumption. So, well, maybe you should have a better look if that's true. That's what they told me. There is no sort of package that you sell together, or there's no reason if I know one type that I would expect the other type to be anything, really. Also, the axis width of a car is independent of the profile of its tires on its wheels. So now we know it's not entirely true, because if you have a very wide axis width, there's probably also a bit wide tires on the car, but they told me that that correlation would be very, very small, so simply ignoring it. So these are two assumptions. Maybe we should have a better look at them and check if they're true, but these are the assumptions I made. Then under these assumptions, you can combine the whole set of probabilities. There's a factor of 2 there because I didn't know whether the A was on the front or on the back. So then you want to put numbers on these probabilities. So the question is, how can you get data for this? Now for the axis width, we have really good data because the Dutch government registered the axis width of all cars. So it took some time, but after insisting for a long period, I got finally the proportion of cars with the same axis width was 20.6%. Then we had our own sort of data set that we collected for an earlier case. So we went out to the parking lot of Amsterdam IKEA and to some rural area which happened to be in the same neighborhood of this crime. And we looked at lots of cars, but we also took a sample of 30 random cars and we photographed them and took all sorts of details. So from this data set, I thought that the probability that cars would be different, had different tires on the front and the back axis, would have a beta distribution with these parameters, 14 and 18. Then I wanted to know what is the probability that if I take a random tire, that it would match the first profile or the second profile. Then I found out that actually there is a car service company in the Netherlands, and they take every half year, they send out a bunch of students to 40 different parking lots, and they register the tire types on cars. So we had a sample in the specific period of the whole of the Netherlands, 40 random parking lots, and random tires for each car. So they had 2,239 cars and so many tires also. Also, I added to this 2 lookalikes because there was another expert involved, and he said, well, I know, he looked at the class characteristics, he said, I know 2 tires that would have sort of similar things, so I added those as well. So to estimate these probability of matching profiles, we started with car service chain data, so more than 2,000 tires. They were of 595 tire types, and we had a sample frequency for each type. Now I couldn't unfortunately give the expert in the case, so that the idea was to give a set of tires, photographs of tires to the expert who didn't know anything about the case, and just have them compare them with the tire tracks on the lawn. And then you could say whether they match or not. But it was too much work to give him the full list of 595 types. Unfortunately, he had to make a selection. So he said about 100. So I took the 91 most common types in the car service chain data. So they had a frequency of 6 or more, because I thought that would cover most of the population. And I added these 2 lookalikes, and that was the list of types I was going to give to the expert. So the expert compared the list to the 2 tire profiles. So the results were a combination of these. So as I said, I took the most common ones. I really regretted that afterwards because it complicated statistical analysis, but you know, you have to make this kind of decision in an hour or so, because I wanted to get this expert going, and I have a deadline for reporting and so on. So, I think if I do it next time, I will take a random sample. So this is what the expert did. He was given a list of 93 types of tires with the 2 marks, and that list included the tires of the tire types of the suspect car. And what he did is simply you can go out on the internet and look at photos of the tire types, and he compared the photos of the internet with each of the marks. And I gave him 4 answer categories. He could either say, well, this is not it, and with a lot of tires he made that decision really quickly. So he compared it and said, no, I don't see anything, you know. And at some tires he studied like a very long time, and then he could decide between, well, it's not a good match but I cannot exclude it, or this is a really good match, or it's somewhere in between. So these were the results. For the suspect's car back tire, I call that type 1, he said there's only one match in this list. And this is the best fit. So it wasn't really a very good fit, but he couldn't exclude it. Certainly couldn't exclude it, and it was somewhere not a good fit, but moderately good. And then for the other, the suspect's car front tire, which I call type 2, he also said it was quite a good match, and it was the best fit in the list. But there were other types, the same tire type but of a different width. He said that's also quite a good match. And this lookalike thing, type number 3, he also said that is quite a good match. And all the other tires, he said, well, they don't match. So this is the results. One type matched for profile 1, now that had a frequency of 1 tire. And for profile 2 there were 4 types who matched, and they had a frequency of 22 in the database. So the 93 types corresponded with the 1422 tires. That's not a random sample of tires, right? So to have a frequency estimate of the matching types involved some statistics. So what we did is we define n as the total number of tire types of the entire population. Now n is unknown, so that's unfortunate. And we define q as a percentage, as the frequencies of those types in the entire population. A priori, we would say it has a Dirichlet probability distribution. And we define ni as the number of occurrences of this type in our sample set. Then n has a multinomial distribution, and the idea was to simulate, put a simulation to derive the probabilities. So you could simulate by from a Dirichlet distribution from this. That is, if you know the n, because I didn't know the total number of tire types, so I had to do something with that. And we argued that, well, there are two sort of estimates for the random tire type to be a non-observed type. And one is this one, and the other one is from good Turing. So you arrive at an estimate of 1095 for the total number of tire types. But I think afterwards I saw Julia's work and the Chinese restaurant process and all sorts of things, and I thought this is going to be, you know, you can do better if you do all sorts of fancy methods on this, and I'd really like to try that.
Also, have you tried like to put a prior over the number of types?
No.
That's also possible.
Yeah, so you can do all sorts of things to improve it. What we did is we worked with this, and then later we tried for different numbers of n. There was no effect basically on our estimate, so that's why I didn't pay too much attention to it. Then you have the distribution of the matches. So we define theta I as 1 if the tire type matches as the indicator. So a random car has a probability of theta of matching. Theta has a prior beta 1, 1. We had some observations of who matched and who didn't, and you could update the prior with that. So we could simulate from a beta distribution for that. So the simulation involved a Monte Carlo simulation for which tire would match, simultaneously for the frequencies. And this would yield, if you sum them all together, you would have the probability that a random tire would match profile 1. Same for profile 2. And we already derived the distributions of that the tires would be different and that they had a certain axis width. So we simulated these frequencies. And we also calculated then this expression for the number of the proportion of cars which would satisfy all the criteria. And these were the results. So here you have the probability distribution of the proportion of cars that has the different tires on the front and back tire axis. This is the distribution of the proportion of cars that would match profile 1, profile 2, and then this is the frequency distribution of the proportion of cars, of the log 10 of the likelihood ratio. So 1 over the proportion of cars and then the log. So as you can see, it varies between 3 and 6 more or less, so it's quite strong evidence actually. So what we reported in the case was, well, we stated the hypothesis, and then we said the car in question matches concerning axis width and tire profile with the observations on the 2 marks. The probability that a random Dutch car matches is about 1 in 50,000. A more conservative estimate is 1 in 5,000. Therefore, it's far more probable, about 5,000 times more, to observe this combination of features when the first hypothesis is true than when the second hypothesis is true. Then the case went to court, and this is what happened. The prosecutor said, well, tire marks could have been caused by the suspect's car. And then the defense said, well, from the tire marks examination, it follows only that it cannot be excluded that the suspect's car was on the crime scene, but, you know, this is true for more cars. And then the court said, well, the profiles of the marks correspond with the profiles of the tires of the suspect's car. And then, unfortunately, they had prosecutor's fallacy. They said the probability that the marks were made by a random other car are conservatively estimated as 1 in 5,000, which yields a high degree of probability that the suspect car made the marks. So that was a bit unfortunate. But then, as I said, there was lots of evidence in the car. In the process, and this conclusion was mainly used as an argument that prior to observing the DNA evidence, which was the real evidence, the probability that the suspect was the offender was already quite large. So I was not too concerned that an innocent person would be in jail because of this prosecution fallacy. So I just showed you this case. Oh, sorry. I have 2 minutes, I guess, for explaining the general. You can generalize this, of course, to other cases and to other types of evidence, shoe prints or whatever type of evidence. So the idea is that you need 3 experts and 2 statisticians. So the first expert would have a quick look at the case and decide, well, we are going to do this or not. Because if it's inclusion, you know, they look at the case and say it's not him, and that's simple. If he says, okay, it sort of looks like a match, well, then you need a statistician to define the proper likelihood ratio, seek some suitable data. Together with the expert, they work together. That's important. They prepare together a test for the first expert. That should be 2 actually, expert 2. And it's important that they avoid expectation bias. So I didn't succeed with that for this expert because he knew, you know, that there was a sort of a match in this set. So that wasn't good, and we should try to improve that if we do it another time. We didn't say it actually to him, but he could anticipate it. And then you need to decide beforehand, before you get the result, what you're going to do with them. So that's also a good idea, I think. So then you need a second expert who completely blind describes the features that he sees in the marks and then compares it with a lot of things. Then you have this expert and the first expert together write a report together with a statistician. And then you need 2 independent experts and an independent statistician to check the whole thing. So who has access to all the details? You need to do that in phases. So the first expert can look at all the details, statistician can look at all the details, but it's very important that the second expert who does the comparison knows nothing. Only when he has to write a report, then he knows about the other things about the case. And of course the people who check it also can have access to the file. So the conclusion is that general error rates, I think, are problematic. You may have general error rates for usually you have very simple cases, but now you have a really difficult case. So what does it mean actually? And also this match-no-match approach is not optimal. We can do better than that. And there's much information inside the head of an expert, and you have to sort of get it out of there. So we propose to think of alternative ways to make the process more objective and transparent. And one of these ways may be blind case-specific tests like we showed here. Thank you.
We might just take one question.
Oh.
No? Well, mine's not that an important question, but I'll ask it anyway. But it's not about the statistics at all. It's just about the testing of the experts. And I felt that there were probably ways in which you could get more information from the expert. I mean, maybe not in this case, but where you can have a rating scale from, rather than those, you had like a categorical response measures. And I don't think that's so good. I think you could have had a rating scale and also confidence measures, and those kind of approaches are much better at actually picking, mapping what the expert knows.
Right.
And I think would actually feed.
Yeah, so my sheet has sort of a space for he could make comments.
Oh, we don't want those.
Oh, you
No,
don't
no, I'm
like it?
joking.
Okay.
But you want, I think you really want a rating scale and a confidence measure as well.
Right.
At least those two things. And comments is great, but I think we know that there's a difference between giving people categorical and versus some kind of more continuous measure. And I think that ultimately you also want a confidence measure in there.
Right.
Their judgment. I think you could, in that way, you might be able to avoid his assumption that there will be, and I think those are shown to be better methods actually.
Okay.
We could discuss it. That's right.
Yes, I'm very much interested in
I have a
that.
psychology question.
I really like to discuss that with you.
Yeah,
Thank
there's
you.
lots of
Yeah.
interesting stuff.
Yeah.
Thank you. One last
Just
question.
real quick. What you described here is what others have described as an evidence lineup, which is to say that you put way more in there. One of the ways that you might get around the bias issue is to actually have two experts, if you can afford them. One where the evidence tire is in the evidence lineup, and the other one where it is not.
Yeah.
And then sort of see how they do that way.
Okay. Yeah. It's great to have all these suggestions because I think avoiding this expectation bias is really important. Yeah. Thank you.